The next topic we have to discuss in terms of reaction mechanisms and energy diagrams is catalysts. A catalyst is a substance that speeds up a chemical reaction without being consumed during the reaction. A catalyst is able to speed up a reaction by lowering the activation energy for a chemical process. Sometimes a reaction occurs too quickly and it needs to be controlled. An inhibitor is a substance that slows down a chemical reaction. A homogeneous catalyst is one that has the same phase as the reactants, while a heterogeneous catalyst is in a different phase than the reactants. The term enzyme simply refers to a biological catalyst. Nearly every reaction that occurs in living cells is enzyme catalyzed. Uses for catalysts include the catalytic converter in a car. This device is responsible for converting the carbon monoxide and nitrogen dioxide in the car's exhaust to less harmful products, CO2 and N2. Many chemicals we depend on for everyday living could not be created efficiently without the help of a catalyst. For example, the efficient production of ammonia requires a catalyst. So does the petroleum cracking process, which produces the majority of the fuel that society demands. And as I mentioned before, all the reactions that occur continuously in every living cell are sped up by the presence of an enzyme. Let's look at an example of how a catalyst works. Once again, a catalyst speeds up a reaction by providing an alternate reaction mechanism. This alternate route from reactants to products requires less activation energy. If less activation energy is required, then more of the reactants will have the necessary energy required in order to form products. Consider the decomposition of formic acid into water and carbon monoxide. The reaction is endothermic, since the enthalpy value is positive. The uncatalyzed reaction is a one-step mechanism. What has to happen in this reaction? The bond between carbon and hydrogen has to break. The bond between carbon and the OH group also has to break. And a bond between hydrogen and the OH group must form. Thus, the activated complex would look something like this. The bond between carbon and hydrogen must break, so draw a slash through that. Same with the bond between carbon and OH. The bond between hydrogen and OH must form, so draw an X on that bond. Okay, so what would this energy diagram look like? Pause the video and try to draw this on your own. Use the information given here in the example. You are given the potential energy of the reactants, the energy required to form the activated complex, and the enthalpy for the reaction. You can do this. Pause the video. When you think you have it, press play to check your work. How'd you do? The reaction is endothermic, so the products should have more energy than the reactants. The hill should rise to positive 60 kcals to represent the activation energy. And remember, the peak of the hill represents the activated complex. The decomposition of formic acid can be sped up by adding a catalyst, HCl. A catalyst does not participate in the overall reaction, so it is not written as a reactant or product. Instead, if a reaction involves a catalyst, the catalyst is written above the arrow for the reaction. The catalyzed decomposition reaction involves two steps, and the activated complexes for both steps are written in the brackets. Step 1 of the mechanism requires 35 kcals of energy. Look at the reactants and products for this step of the mechanism. What has to happen to the bonds represented by the dotted lines? Well, this CO bond must break. This will result in the formation of COH, one of the products. The bond between O and H must form. This will eventually lead to the formation of water, because the bond between hydrogen and chlorine has to break in order to form the Cl- as a product. Step 2 requires 25 kcals of energy. What has to happen to the bonds represented with the dotted lines in this activated complex in order to form products? Well, the bond between carbon and hydrogen has to break in order to form CO. And the bond between H and Cl must form in order to form HCl. Now, step 1 and step 2 must add together to form the overall reaction. Notice that CO is a product of step 1 and a reactant in step 2. Therefore, COH will cancel. The same is true for Cl-. It is a product of step 1 and a reactant in step 2. It will also cancel. COH and Cl- are intermediates in the reaction mechanism. Any substance that is produced in one step and consumed in a subsequent step is referred to as an intermediate. HCl is a catalyst. Notice HCl is a reactant in step 1 and a product in step 2. That means HCl is not consumed by the reaction. Any substance that is a reactant in one step and is produced in a subsequent step is, by definition, a catalyst. All right, let's draw the reaction coordinate for the catalyzed reaction on the same axes as the uncatalyzed reaction. The reactants will still start with 0 kcals of energy. Now, since this is a two-step mechanism, the energy diagram will have two humps. The activated complex in step 1 has an energy of 35 kcals, so the first hump must go up to 35. The second activated complex has an energy of 25 kcals, so the second hump occurs at 25 kcals. The products still have 10 kcals of energy. Here are the activated complex for steps 1 and 2. Now let's label this catalyzed reaction diagram. The activation energy forward always relates to the highest hill or hump in the diagram. Step 1 has the highest hill, so the activation energy forward is 35 kcals. 35 kcals minus 0 kcals. Notice that delta H for both the catalyzed and uncatalyzed reaction is positive 10 kcals. A catalyst does not affect the enthalpy of the reaction. A catalyst simply lowers the activation energy. The activation energy for the uncatalyzed reaction is 60 kcals. However, the activation energy for the catalyzed reaction is only 35 kcals. All right, here we go. Pause the video and try to answer questions 1 through 7 concerning the energy diagrams for the decomposition of formic acid. After you have completed the questions, press play to check your answers. What is happening at the activated complex in the uncatalyzed reaction? Well, the CH and CO bonds are breaking, and the HOH bond is forming. What is happening at the activated complex in the catalyzed reaction in step 1? The CO and HCl bonds are breaking, while the HOH bond is forming. Why would the catalyzed reaction be faster? A catalyzed reaction has a lower activation energy. Therefore, more reactant molecules possess the necessary energy to form products. What is the catalyst in this reaction? The substance written above the arrow, HCl. Is it homogeneous or heterogeneous? The reactant formic acid is aqueous. HCl is also aqueous. So this is a homogeneous catalyst. What would happen if sulfuric acid was used instead of HCl? Well, sulfuric acid is H2SO4, so it has twice as many hydrogen atoms that could collide with formic acid in step 1 of the reaction mechanism. The rate of the reaction would increase even more because of this.